In 5.5, we are going to be using everything we've learned about logarithms and exponential growth to solve real-world problems. So, jumping right in, some common math models for exponential growth and decay. So if you have any situation that is growth or decay, we can use this, y equals a e to the rt. Exponential decay is the same thing, it's just r is going to be negative. You actually don't need to memorize two different formulas because it's essentially the same thing, just if the r is negative, it's decay. If the r is positive, it's not. It's growth. Now, this should look really, really familiar. It's the PERT equation, just instead of PERT for principal, since that's talking about money, we use A for the initial amount. So this is the PERT equation, essentially. The other ones, I don't think we have any problems that deal with it. I know we do logistic growth in calculus next year, but when things grow exponentially, like bacteria, or if you're talking about like the population of rabbits and rabbits are growing exponentially, in the real world, that exponential growth doesn't continue on forever because there's restraints in the environment, like the rabbits run out of food or the bacteria, consume all the available resource. So in the real world, we have this thing called carrying capacity. So our population it sometimes even goes out above that, but then it drops back down and settles to that carrying capacity. So anyway, so this is a logistic growth model. It's more of what happens in the real world, and that's the equation. So you can see the PERT equation kind of embedded in there. Again, we don't have problems with this year, but you will see it again in calculus. A Gaussian model is here. Those of you who are in statistics, this should look really familiar. This is a bell curve. And so this is the equation for a bell curve. If you ever take a calculus-based statistics course, you'll do all kinds of stuff. Like in statistics, we find the area under the curve, and we have formulas and calculators that do that for us. It's actually a calculus problem that underlies the whole thing. So anyway, we are not doing anything with Gaussian, but it pops up a ton in higher level statistics course, not the one that you're taking now. Okay, so we are going to do some problems here. So estimates of the amounts in billions of U.S. online advertising spending from 2011 to 2015 can be modeled by this lovely equation. S is the amount of spending in billions, T11 is the year 2011. So we want to know how much was spent in 2001. And then, when will the amount of U.S. online advertising spending reach 100 billion? Okay, so let's answer the first question. How much was spent in 2001? So, we're looking for S, the spending, how much was spent. And we have 9.3 e to the 0.1129. And if we're looking for 2001, that is t equals 1. So we're just going to plug in 1 here. I don't really want parentheses. Times 1. And we're just going to plug that into the calculator and hope that our calculator tells us lovely things. 9.3 e to the 0.1129. And it looks like we have 10.4. So this is 10.4 billion. Sounds pretty easy. Okay, second question. When will the amount of advertising reach 100 billion? So we want to know, when is our spending going to reach 100 billion? So we have 9.3 e to the 0.1129 t. Okay, we want to solve this for t. So the first thing that we're going to do is divide both sides by 9.3. And I am not going to put anything in my calculator until the very end because I don't want to introduce any rounding error. So I'm just going to leave that as 100 divided by 9.3. And we have e to the 0.1129t. Now, in order to solve this, you can either write it in logarithmic form or you can take the natural log of both sides. The reason we would want to take the natural log is because our t is in the exponent, and when we take the natural log, we can use the down and front property. So we have natural log of 100 divided by 9.3 equals 0.1129t times the natural log of e. Well, the natural log of e is just 1. We don't need that anymore. That's gone. And now to solve for t, we're just going to divide both sides by 1129. 0.1129, that's what I meant. So now we've got the t by itself. All we have to do is plug all of that into our calculator. So we're going to pick up our calculator and do that. And I think we end up right around 21. So in 21 years, or in the year 2021, we can expect online advertising spending to reach $100 billion. All right, let's take a look at this one. The number of bacteria in a culture is increasing according to the law of exponential growth. Okay, so that means whatever model we have here, it is going to be y equals a e to the rt. Or if you're a really big fan of the PERT equation, go ahead and use PERT. It's no big deal. After 1 hour, there are 100 bacteria. Bacterial, who wrote that? Bacteria. And after 2 hours, there are 200 bacteria. We don't know how much bacteria will there be after 3 hours. Now, some of you are probably tempted to be like, oh, 1 hour 100, 2 hours 200, 3 hours, it'll be 300. No, this is not linear, it's exponential growth. So we need to use this model. So let's plug in what we know. We know that after 1 hour, we have 100 bacteria. So let's see. We don't know the rate of growth, but we do know our time. After 1 hour time, we don't know the initial amount. We have 100 bacteria. So we know that 100 equals a e to the r. Okay, what else do we know? After 2 hours, there are 200 bacteria. So, again, we don't know A, we don't know our rate, but after 2 hours, we have 200 bacteria. So we have 200 equals A e to the 2r. Okay, so here I have 2 equations and 2 things that I don't know. I don't know the A and I don't know the r. So what I'm going to do, I'm going to go back to this green equation and I'm going to solve the green equation for A and then use substitution to put it into the red equation. So let's do that. So A equals 100 divided by e to the r. And now we're going to plug this in for A over here. So 200 equals 100 over e to the r times e to the 2r. And let's see, e to the 2r and e to the r, we can subtract those exponents. So we get 200 equals 100 e to the r, because even the 2r minus r is going to be r. We divide both sides by 100, and we get 2 equals e to the r. And we are so close. If we take the natural log of both sides, we can go down in front, and we get the natural log of 2 equals r natural log of e, which just cancels out. So r is the natural log of 2. That's exciting. What is the natural log of 2? Let's find out. Natural log of 2. 0.693. Great. So r equals 0.693. So if we go back to this blue equation, let's find it. There it is. I'm going to rewrite it over here. We know y equals r is 0.693 t. Now, I left a little blank there because we still don't know a, but come back over here. See, we have a equals 100 over e to the r. So we already know what r is. We just found out. It's 100 over e to the natural log of 2, or the 0.693. E to the natural log of 2, the e and the natural log kind of cancel each other out. So this is 100 divided by 2. So a is 50. Okay, so this equation, this blue equation, models what's happening with our bacteria. We started with 50, and this is the rate of growth, 0.693. So the question was, how many bacteria will there be after 3 hours? So we can do 50 e to the 0.693 times 3. We're going to put that into our calculator. And when we do that, we find we are right around 400 bacteria.